Alrighty, so welcome to class. Too bad Ted's not here, huh?
He's here.
He hasn't shown up yet. He'll show up. He always shows up. Okay. So today's lecture is really short. You notice the slides are really short, but that's because I'm going to spend most of my time doing a demonstration in this dumb screen. That's better. Okay, so while I'm going over some introductory stuff, I put a lecture notes folder, and in here we have the Monte Carlo Pi. And so if you want to follow along while I'm doing this, you can download these two files. And that goes for you at home too. So now we're going to start on the fun stuff. So we're actually going to talk about parallel computing. And specifically, he's made it! Yay! Okay. So I don't feel completely lonely.
Thanks.
You don't count, Robbie. I'm sorry. All right. So far, all we've talked about mainly is a lot of hardware and a lot of optimizations, just simple things to look out for, and some more advanced things that I covered last time. And there will be a quiz. I'll be putting that up today or tomorrow on all that stuff. Okay, should be fairly simple. Shouldn't be too big a deal. But today we actually get to start on the fun stuff. So we're going to talk about parallel computing. So in the book, there is a chapter 4, and I was considering just going through chapter 4 today, but that seemed really boring. And so I'm going to pick up bits and pieces of chapter 4 while we go through the rest of the chapters. And so there's a couple bits and pieces I'm actually going to cover today. So the first thing is section 4.2, 4.2.1, and I think that's it for today. Those are the sections I'm going to be covering from chapter 4. And then we're going to be going over chapter 5, which talks about the basics of OpenMP. Okay, so back to the hardware in chapter 4 though. Shared memory hardware. Basically, this is your typical modern multi-core desktop computer, laptop. Usually 4. If you have hyper-threading, your operating system says you have 8. So anyway, on King's Peak, they have nodes that have up to, 64 cores or something like that? Anyway, and those are shared memory machines. One node on the CHPC consists of multiple cores, and they all share the same memory. They all have access to everything. The other paradigm is called distributed computing, in which you hook up two computers through the internet. Now, computer A cannot access the memory on computer B, and so that's called distributed memory computing. In this case, we're talking about a single machine or a single node. And so you have your, that's wrong. So you have one socket, maybe 2 sockets, and that's all on a node. Okay, so there's our big node. And then inside of that, you have multiple cores, okay? And they all have access to the same memory address space, okay? So here's the RAM. And so this would be 2 sockets with 4 cores apiece, so we have 8 cores total for this imaginary machine. So that's basically what we're looking at. Okay, it's your typical computer. Now there comes when you're doing parallel computing using shared memory, we run into a problem called cache coherence. Okay, because what color am I using? Red. Okay, let's use a different color. Green. Okay, so let's say we have some value in our memory here. And let's say this guy, he wants to use that value, so he pulls a copy of it to his cache. Okay, and this guy, well, he also needs that value, so he pulls a copy of it here. So now what happens if, say, value this gets turned into the letter A. Let's say it started as a Z, and this guy turns it into an A, and this guy turns it into the letter C. Now we have 3 different copies of the same thing that are all different. Okay. Now, modern hardware does not allow us to do this. Okay, because there is another device in between the two. Okay, and its job is to maintain what's called cache coherence. So, let's say A gets modified first, and he flushes that value, is what it's called. He flushes it or writes it back to the memory. As it passes through this magic device says, hey, you need to change that value. That's now an A. Okay? So the reason why this is important is because this eats up time, it eats up bandwidth, because it has to, tell everyone what's going on. And so you can end up in a situation called false sharing. Where everybody's trying to modify the same thing at once, and this little guy gets overworked because he's got so much stuff to do. Okay? And so that's just something to be aware of as we proceed. So that's the hardware end of things. And so then we need to talk about why are we parallelizing this in the first place? Okay, I guess there's a number 0 because it's cool. Okay, but the 2 important reasons. 1, because we can. That's a good reason too. 1, because we need our program to go faster. For whatever reason, it's taking too long. We need it to go faster. The other option is we need more memory. We need to do larger problems. Okay? And both of these have very different approaches. Usually if you need more memory, you have to go with a distributed computing approach. Whereas if you just need it to go a little bit faster, you can go with the shared memory approach. And when we are measuring our parallel programs, there's a specific metric that they call scaling. And we want to know how well does our program scale. And there's 2 different ways to measure this. One is strong scaling, and one is weak scaling. So strong scaling says, all right, let's, strong scaling. This says if with one processor, it took one processor, size n, took t amount of time, so we had one processor, and it took some amount of time. Now, if we use 4 processors on the same problem with n data points, then it should take t divided by 4 amount of time. Okay, so that's called strong scaling, which you see is related to we need it to go faster. Now, weak scaling is related to point number 2 here. So it says if we have one processor on size n, on a size n problem that took t amount of time, then if we use 4 processors and we quadruple the amount of work, it should take the same amount of time. So we've added 4 times the work, 4 times the people working on it, should get it done in the same amount of time. Now this is all theory, okay? This doesn't actually happen in practice, but the better you're scaling, the more processors you can use without your program blowing up. Not blowing up, but slowing down. Because, just so you know, if this is, say, your speed up, and I'll talk about this later, a little bit more later on, but if this is your speed up and this is then the number of processors, what we would like is something that looks like that. As we increase the number of processors, we get to go faster. However, what usually ends up happening is something like this. And in horrible situations, it can go like this. Okay. So the third one is really bad, and you can do that if you're not careful, if you don't understand what you're doing. Okay. So now we get to talk about OpenMP. OpenMP is a standard that's implemented by several compilers, most notably Intel and GNU. It's a shared memory parallel programming. It's available for Fortran and C or C++. You have to compile your program using the appropriate OpenMP flag. I don't know what it is for Intel, but it's this one here for the GCC. And what it does, there's actually lots of ways to write multi-threaded applications or parallel programs. You could use the internet if you really wanted to. You could do that. But OpenMP was developed for us poor, non-nerdy scientists and engineers who don't want to delve into the details of networking and communications. And so they tried to simplify it for us a little bit. So I found this really great tutorial that you're welcome to look at on the basics of OpenMP in specifically C or C++. Most tutorials that I've found tend to be in Fortran, but since everybody seems to be using C++, that's what we're going to focus on now. On Canvas, I have posted useful PDFs, an OpenMP for Fortran tutorial right here. And then there's this one. I don't even remember what this one is, but it's called OpenMP-C++. So maybe it's useful. Oh yeah, same thing in PDF form. So there you go. Anyway, so back to where we were. So OpenMP uses what they call a fork join model. Basically, this is the way it works. If this is your program, come on, draw for me, please. If this is your program, the program is going to start with one thread, as they call it. Okay, there's one process. And he's going along until we hit a line that looks like this. Okay, at which point it forks into multiple processes. And those multiple processes then run through your code until we come to the end of the parallel region, at which point the three join back together and we're left with just one process. Okay, any questions on the basics of that?
So that line, that's like a legitimate line of code?
It is a legitimate line of code.
That is for C++ or?
C++. Yeah. So at this point, the plan is to switch over to here. Okay, so this is actually, I'm going to give you a demonstration on how to parallelize a code using OpenMP. And it's actually homework problem, where is it? 6.2. So 6.2 says, here's a, maybe you can see that, maybe you can't, it might be too dark. But basically, it's a way of calculating pi using a Monte Carlo method. Okay, so if you take your circle, take a unit circle and surround it by a square, okay, and you generate random numbers inside this square, and then you count the number that are inside the circle and divide that by the total number of points, that gives you the number pi. Does that make sense? A little bit? Anyway, so the homework problem is to write a parallel OpenMP program that does this. Okay? So what I have here is a serial version of this program. And I'm just going to show you how long this takes to run. So this is just doing it 5 times to kind of
10 million points?
Something like that. It's a lot of points. So I'm generating 10 million points, calculating how many of those points are inside the circle, and from that we can calculate pi. Unfortunately, you can see, due to the randomness of the Monte Carlo method, we really only get the first 3 digits. Because after that, they start changing. And so that Monte Carlo methods tend to be like this. They converge very slowly. We're using, like you said, 1 billion points or something, and we're getting only 3 decimal places of pi. So, we actually don't need that line anymore. So I wrote a function here, calc pi. I give it the number of random points to use, and it spits out its estimation of pi. So in here, we set pi equal to 0, and then we have our random number generator. Now, if you're using C or C++, you may have seen or used the function called rand, and its accompanying function srand. You may or may not be familiar with this. But this is kind of the default random number generator. The problem with rand is that it is not thread safe. You cannot have multiple threads use it at the same time. And different implementations do this in different ways. But the reason is because inside the function it has a single variable that is static, so it sticks around, and it changes. Every time rand gets accessed, that variable inside of rand changes. And so if you have multiple threads trying to access one variable at the same time, we end up with what's called a data race condition. It depends on which one gets there first. And on top of that, if both try to access the variable at the exact same time, you can get garbage, a number that's not a number, because you get half of the first number and half of the second number, and you can just get garbage out of it. And so whenever you're using functions, you need to know if it's thread safe or not. Okay, but anyway, in this case, C++11, okay, so the 2011 standard gives us a much better option. Okay, it gives us in the random header file a bunch of random number generators. This is called the Mersenne Twister random number generator, and we are going to seed it with the time. And I know this is really long, but I spent like 2 hours today trying to figure out the best way to do this. As far as I can tell, this is the best way to do this. Okay, so we use the high resolution clock. We tell it what is the time right now, and then we turn that into an integer that the random number generator can actually use. And so the seed tells the random number generator where to start from. And when it starts from, and from there, it does its math and magic and makes a whole sequence of random numbers. But these are actually called pseudo-random number generators because they're not really random. They depend on the seed. If you give it the same seed every time, you get the exact same sequence of random numbers. And so that's why we use the time. That's about as random as we can get, really, is what time is it now? Down to milliseconds. Okay? So if we change the seed, we change our random numbers. Then we generate a uniform real distribution, and we tell it we want doubles out of this. And I call it square, and I tell it I want these numbers to be distributed from 0 to 1. Okay, that's our square that we're going to be generating these in. And it has lots of different distributions. It has, uniform Gaussian distributions and chi distributions, and it's got tons of them. But depending on what distribution you want, there you go. So this is a uniform real distribution. You can do a uniform integer distribution if you just want integers from like a die roll from 1 to 6, something like that. Anyway, and then this is a little convenience function. We can bind the two together. I don't really know how this works, but it's convenient. So we combine them together into this one thing. So now we've taken the uniform distribution. It's using the random numbers generated by our Mersenne Twister algorithm. Okay, so now here we have the sum. This is going to count all of the points inside of the unit circle there. And some helpful variables. So now we loop through from 0 to n, and we say, all right, give me an x coordinate, give me a y coordinate. We calculate the radius. If that radius is less than 1, we add 1 to sum. Okay, and we do that for all of them. At this point, we can then calculate pi. Okay, so pi equals 0. We add sum to it, and then we multiply that by 4, and we divide by then the total number of points used, at which point we have our estimate of pi. Okay, so now the question is, how do we turn this into a parallel program? First off, we have to include that. Okay, so that's the very first thing you got to do, is to have that. And let's see, how long did this take? You just got to keep this in mind. This took 14 seconds. So the way this works is you're going to put in pragma OMP parallel, and there's a handy little what's the word I'm thinking of? Attribute, I guess, we can put on it. And then we put a brace. And so the brace opens up the parallel region. All right? And we're going to want this parallel region to run all the way to here. Right? Sounds about right. Okay, and I'm going to...
So that's just inside the calculate pi function, right?
Yeah, so this is inside of the calculate pi function.
Okay.
We'll just indent all that to make it look nice. Alrighty, so now I mentioned that the rand function is not thread safe. And so we have, let me just talk it through this way. We have the master thread. He enters the function. He comes in and he hits now our parallel region, at which point I said I want it to split into 2 threads. So now we have 2 processes that are running through this code. Okay, so we construct our random number generator. How many random number generators do we get now? There's 2. Exactly. There's 2 of them because we have 2 threads. Each thread has its own random number generator. Here's a question for you. How many pi's are there?
2. Oh no, there's just 1.
There's just 1. Okay, so pi is shared. It's shared memory. Both threads are going to use the same value of pi, or the same variable, which can lead to a data race condition later on. So that's something we're going to have to account for.
So if they're both, okay, because I guess they can both write to pi, right?
Exactly. Okay, so that's a problem.
Well, it's a problem, but only if you use it wrong, right?
Yes.
Okay, because it has to be that way for this.
Yeah, exactly.
Okay.
So here's another problem. We have this function here that is asking what time is it right now. Now, what happens if both threads do that at the exact same time?
Well,
Be generating the same.
They'll be getting exactly.
Half a set of random numbers, I guess.
Exactly. They'll be generating the exact same random numbers. Twice. Which isn't very helpful to us. Because that's just garbage. So how do we account for that?
So does it only have, because I don't really understand how that works, but does that only call the time once? So it's not like you have to worry about them overlapping throughout the whole thing, it's just at the beginning? Is that how that works?
I'm not sure I understand your question.
So you're worried about them calling that time at the same exact time.
Mm-hmm.
Do you have to worry about that only once, or is that going to happen many times throughout the program?
So in this function, it's only going to happen once. The function gets called multiple times.
Okay, that was okay.
Okay. So how do we account for this then? Well, OpenMP provides us a nice little solution. We're going to have an integer called an ID and get thread ID. So every thread has an integer value associated with it. Thread 0, thread 1, thread 2, and so on. So now we have an ID number. And so we're just going to take this integer. This is what this is outputting. This is outputting an integer, and we're going to add the ID. And so now they have 2 completely separate seeds, so we're getting 2 different sets of random numbers. Okay, so now each one of these has its own uniform distribution variable. Each one has its own sum variable, and these variables are also separate. Okay, so all these variables that I've declared inside of here, these are called private variables. They're private to a single thread. No other thread can access them. It's impossible. It's forbidden by the standard. But we still have this pi out here that's shared. Okay, so now, how do we? What are we trying to accomplish by running this in parallel?
Make it faster.
Make it faster. So, what part of this do we actually need to try and make faster?
The loop.
It's the loop. Okay, so in order to make the loop faster,
Just divide n by 2, right? Or n by however many processors.
we could do it manually like that. Yes. Okay, so your suggestion is, let's say, let's see here. ID times n divided by the number of threads. Something like that. I'm not going to actually do this because there's a better way to do it. But yep, that's it. Times n divided by the number of threads. At which point we then put this in here. Okay. But we don't actually have to do this ourselves. OpenMP provides some nice little pragmas.
What is that? What is pragma?
Pragma is defined in the C and C++ standards as notifications to the compiler. Okay? If the compiler does not understand the pragma, it will ignore it.
Okay, so you don't know if what you're telling it is actually getting caught by it.
Well, you have to know your compiler.
Okay.
So in this case, I do know my compiler, and it understands the OpenMP pragmas. So on the line right before there, we put the pragma OMP4. Okay, so we have these two threads. They're running through the code, and then they hit this. At this point, the two threads take two separate chunks of this loop. They each run their own individual chunk.
Can you only do that with for loops?
No, but it's the easiest.
Oh, okay.
So we're starting out easy.
That would make sense. In fact, I don't even know how you do that with other types of loops.
You do it using what's called tasks. And I haven't come up with a good example for tasks yet, but working on it. So each one, this loop basically now gets divided in half. It's run at the exact same time. You'll notice each one is now calculating two individual sums. So now the question is, after we get through this loop, both threads have finished their piece of the loop. They've calculated their own sum variables. How do we get those into pi? And the answer is with what's called a critical region. So a critical region looks like this. So what critical means is only one thread can process this at a time. That's how you prevent data races. You prevent them trying to write to the variable at the exact same time. So basically what happens, these two threads, they get through the loop, and then they come to the critical region. The one that gets there first gets to go first. First come, first serve. So the first guy starts going into here, and the second guy, he stops and waits. He stops and waits right here until it's his turn. At which point he goes and runs through the code. Okay? And now we have this. So here's the end of our parallel region. Right here. What do you think is going to happen here?
Doesn't that need to be inside the critical region as well?
Needs to be inside the critical region. Why?
Well, because if not, multiple stuff is trying to write to it at the same time.
Okay.
Processors trying to write to it at the same time.
Good. That is correct. Except this
And it's dependent on itself.
value here should only be computed once. If we put it in the critical region, it'll be computed twice. So it actually needs to come out
Oh, I see.
of the parallel region, so it's only computed by the master thread. Okay, and that is we just turned our serial program into a parallel program, running 2 threads. And, oh, looks like we had a problem there. Get thread ID was not declared in this scope. So, where did I screw up? Oh, thread num. Sorry. Okay. Well, we can fix that. All right, so that compiles. You'll notice that I'm using the C++11 standard so we can get our random number generator. And I'm compiling with the FOpenMP flag.
Are we going to have to do that as well? The C++11?
If you want to use these nice handy dandy random number generators.
Okay.
Yeah. And so now we're going to time our Pi program. So that took, in serial, it took 14 seconds. In parallel with 2 processes, it took 7 seconds. That seems pretty good to me.
What's the user?
Oh, don't worry about that. The only one you need to worry about is the real time. If you'll notice, though,
Is it saying that that's adding both of them?
it's adding both of them together.
Okay, so it's about the same.
Yeah.
It's actually longer.
It's actually, well,
A little bit. Very, very.
that's what we're going to call operating system noise.
Okay.
The operating system and all the other programs running on your computer, they screw everything up. So they interfere, you know, they try and start and they try and stop, they run their own stuff, and so they can cause noise, which makes timing your programs very difficult.
So running it on more processors is as easy as changing that 2 to a 4 or whatever you want to change it to?
Yep, and you don't even have to hard code it, I don't think. But I don't want to run it on 4 because the virtual machine is using 4,
Oh, okay.
and that would, you know, kill your computer to not have at least one left open. Now what is 14 divided by 3?
4.2333.
14 divided by 3. 4.6.
Oh, yeah.
Close.
That's what I meant.
So that's pretty close. Let's run it again. Okay, now we've got about the same. Okay, so 5. So why aren't we getting 4.6? Why are we getting 5?
Because it's not exactly able to. It's not 1-to-1. I don't know how else to say that. There's stuff that it's doing in serial still.
Exactly. It's because there's several things going on here. First off, this here is all run in serial. This is called your serial fraction. Okay. So there's your serial fraction.
And it has to wait in that critical area.
Okay. Yes, you are correct. I'll go back down here. They have to sit and wait for each other in this critical area. This critical area is serializing your code. Okay? Because you can't process things at the same time. You have to sit there and do things one at a time. So that makes it slow down. Another thing, every time you enter a parallel region, there is an overhead. It has to set up 3 threads now and initialize all their variables and yada, 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 do a bunch of stuff that we don't really care about. But the point is it's there, and it takes time. And then ending the joining process also takes time. And so that all of that kind of stuff is serializing your code. And so your scaling isn't going to be perfect because we have these serial portions in there. It would be better if there was more work to do in the loop. But this is actually a super easy loop. There's not a lot of work to do, and so it just doesn't, I don't know what to say about it, but because there's not so much work to do, your scaling is going to be really low. The more stuff you can do in parallel without data dependencies or critical regions, the better. Now there is one more thing that we can do. We don't need this critical region. And I got to remember exactly how to do this. Because OpenMP provides what's known as a reduction. So we can take a shared variable and accumulate. So whenever it goes into this for with the reduction here, we tell it we want to multiply all of the fac variables here. And so fac is shared in this example. And when it enters here, it's going to make fac private, so everyone gets its own copy. It's initialized to either 0 or 1, depending on what operation you're doing. Since they're doing a multiplication, it initializes it to 1. And then you do some stuff, and when the loop is over, it takes all those private variables and multiplies them all together into the shared variable. And we can do the same thing in our loop. And I actually didn't test this, so, scary, it may screw up. But we can say, we actually don't need the sum variable at this point. We can just say pi, which is shared, right? Pi is equal to 0, okay? And we say pi plus plus, and we put here the reduction plus colon pi. At which point, we are done with the parallel region.
So does it do that just, where does that occur? Just after the for loop?
Right. As soon as the for loop is over and everybody's finished, I should note also, for loops by default are blocking. Okay, what that means is that once a thread is done with its section of the loop, it's going to stop and wait at the end of the loop for everyone else to finish. You can add another clause, that's the word I was looking for earlier, clause, called no wait, which, however, no wait and reduction don't mix. So, because a reduction implies you have to stop and wait for everyone to finish. So that blocking will also screw things up or slow down your code and reduce your scalability, your parallel scalability. So let's see if this works. Compiled, so that's always the first step. There we go. That looks a little better. Oh, we got below 5 that time. Let's see if that is consistent. No, it's not. It's just noise. But it's also easier because you don't have to write your own critical region. So that's pretty handy. So important things I wanted you to take note of or to learn about. One is the parallel region. The for loops. Private clause I didn't talk about. Private clause is more useful in Fortran because in Fortran you have to declare all your variables at the top. You can't just throw them wherever you want. But since C++ 11 or since C++ lets us do that, anything declared inside the parallel region is a private variable. This is really important, especially when you're generating random numbers, to know how to do that correctly. And random number generation is a whole nother world, but hopefully what I've given you will be useful enough. The critical region and then the reduction clause. And my last little note here, the default random number generators are typically not thread safe. So hopefully that was kind of interesting to you about how all this works. This is not an assignment, okay, but it is a suggestion. We'll say that. They have an example problem, section 6.1.3, a parallel integration to calculate pi. Okay, so try and just give that a try. See if you can get that to work. And anyway, we'll go ahead and finish up there. So, any questions before we finish?
What was the example problem? Sorry.
6.1.3, it's a parallel integration. I just lost it again. Yeah, 6.1.3, page 147 is what I have here. And they give a Fortran version example of how to do it. So anyway, there you go. Alrighty, so we'll see everybody on Tuesday. And first project's due this Saturday, next project's due on Wednesday. Because then we get to redo that project using OpenMP. So, have fun everyone.